let y be an integer value random variable of mean, mu, sigma squared. All right, instead of just reading it out, let me at least give a picture. So in general, our random variables say for h of yn, that is the image of an n-digit number. It's basically flat until a very small peak. And so our j in the original lemma would be way too big. And what I'm saying is that let's ignore these outside tail parts. Let me just consider the part like close to the mean. Then the probability that I am in this part by Chebyshev's inequality is at least, say this is the mean, mu, and then I go lambda sigma away from the mean, then the probability that you're in this part here is at least 1 minus 1 over lambda squared. And so, I mean, the proof of this lemma is just apply the first lemma on this smaller interval. And so size of j, in this case, would be, so I go lambda sigma out, so it'll be 2 lambda sigma plus 1. All right, and so, I mean, this part here is this is the loss due to applying Chebyshev's inequality, and this is just the statement from lemma 1. This is size of j. Size of j minus 1.
Yeah, but Chebyshev is a very weak inequality, so maybe you can improve it, because in UK you have a much more arbitrary distribution.
Y is a positive random variable too, yeah?
Yeah, I mean, h of y, yeah. I didn't give all the, I mean, in our case it works, because h of yn is going to be positive numbers. The h of right? And you're right, I can certainly improve this, but for my purposes, this was enough. I mean, my end result is, I mean, the loss is like 1/1,000,000 of a percent, so this was good enough. Okay. And so now I need a natural way to shift my random variable. Because the problem with, let me just jump back. The problem with this lemma, if you imagine adding one more digit, so if I'm comparing h of yn with h of yn plus 1, so I'm adding one more digit, then, I mean, the mean has shifted by mu, basically, the digit mean. But these aren't the same random variable anymore. So I can't, in terms of this lemma, like, just because these aren't the same random variable anymore, this lemma doesn't really help me. And I mean, the goal was to use the local limit law to say that, okay, these random variables are actually very close to each other, just basically shifted by a factor of mu. But that doesn't work yet again. So I need another way, a natural way to be able to shift my random variable. So here's an example. So consider these three intervals, and I'm considering the random variable, just randomly choose an integer in each interval. Then under my map h just shifts these intervals by exactly 1 and 2. So I mean, these are the same interval, but I have these extra ones here. So when I take h of it, the same thing's happening, but I always shift by a factor of 2. So does everyone agree with that? Okay. And I want to use this idea to in combination with this lemma, to construct intervals with high density. So in general, I'm going to let b of nk be this mess. What b of nk is just, it's an interval of numbers where the first k digits are all 1, and then then I have n over 4 minus k zeros, and then the rest I just let to be random. So in our case, say like this one, this would be b of 8 comma 2. And h of these intervals is just, okay, if y sub nk is randomly choosing an integer in b sub nk, then the image of h of y sub nk is just y sub 0, but shifted by k. And this works perfectly with the lemma that I just mentioned. So let me revisit. So again, our goal right now is we're not going to construct, I'm still not saying anything about the density of intervals of this type. But I'm getting smaller intervals. I'm getting subsets of these, which will be high density. So remember, we had from 10 to the 400 to 10 to the 401. We had about 18% density in this interval. And what I'm going to do is I'm going to choose n such that, I guess, the mean of the expected value of h of y 3n over 4 lands in this interval, is approximately 10 to the 400. So I'm saying pick n such that a random 3n over 4 digit number is, so the expected value of this random variable lies in here. So we'll say this will be h of y sub 3n over 4. And then what I can do is I can add ones as I please to shift this interval, or to shift this random variable. I can shift it up to n over 4. And this gives me a window to say something exactly about, or to construct an interval with a large density of happy numbers. If I knew that there was an interval in here, say I, and I had about 18%, then, I mean, by this lemma, there's a shift of this random variable, say tau sub k of, let's call it y, that hits happy numbers in this interval with about 18% probability. And because, I mean, and that means that the interval, say, let's say that k equals 10 worked. Then the interval, this interval is going to be, we're going to have 10 ones. 1, 2, 3, 4, 5, 6, 7, 8. We're going to have 10. And then I'm going to have n over 4 minus 10 zeros. And then the rest of the numbers are just random. So I'm considering this interval of integers. What it means is this interval will have about 18% of these numbers will be happy. And so this this 3n over 4, that was kind of arbitrary. I just sort of, let's just fix the first n over 4, and then let the remaining 3n over 4 vary. I could have done just a different fraction. All that really matters is that I did it bigger than a half. And that's coming from this. It's sort of a game playing like I'm choosing how big J should be such that this error estimate is manageable. But okay. All right, so this, is there any questions that can make this a little bit clearer?
You're just like getting intervals further out with the same density, right? They're not getting bigger.
Yeah. And again, so this interval, okay, like what would n be such that the image of this is landing here? N would be, I mean, it would be approximately we need n times 3n over 4 mu to be approximately 10 to the 400. So this n is going to be huge. I mean, it's going to be around, 4 over 3 mu, 10 to the 100, or 10 to the 400. That's how many digits I have. So this interval, again, I'm confusing people by writing the interval notation. I'm saying x in this interval, for x in this interval, x will have this form. It will have, k1s and then n minus k. 10 ones will have n over 4 minus 10 zeros, and then the rest of the integers will be random. And so this interval I is going to be subset of 10 to the n minus 1 and 10 to the n. And n is going to be around this size. And I will have density of happy numbers about 18%. And so this is a process I can actually iterate. And I can get exact bounds on how much I lose each time. So I lose like, almost nothing. So you just have to trust me on that. But, okay. And so, I mean, this is just sort of rephrasing what I just said, but probably not any better. And we're just, I'm not going to repeat all this. So. But this is the loss. So I didn't mention lambda. Again, lambda is sort of like, okay, the image of this is a bell curve. The image of this interval, does everyone understand like what this interval is? It's all numbers of this form. It is 10 ones, n minus 10 zeros, and then h of this interval, or h of like, let's call it y. If y is the random variable, choosing a random number in this interval, h of y is some bell curve. And I guess where this bell curve lands, this whole interval j is much too big. And so lambda is where I'm using Chebyshev's inequality to say, okay, let me look at a restriction. Let me look at where the bulk of this lands. And then applying this, this j over, size of j over size of I is going to be much better. So. And iterating this process, here's at each step, I'm losing this much. This is from Chebyshev's inequality again. I'm basically always picking lambda to be about, I'm always picking lambda to be about 10 to the n over 8. And so I can't pick lambda too big, because then as lambda gets bigger, that j in that lemma becomes too big. So I always try to set lambda to be 10 to the n over 8. And then at each step, this is what I lose from Chebyshev's inequality. And this is just that lemma, but I rewrote it in a slightly cleaner form. This will be strictly less than what I get from that lemma. And so I can estimate, okay, this is the error I lose at each step. And as I repeat this process, I multiply the errors. So total error is going to be at most this much. And so I can get an infinite sequence of intervals. And every single one of these intervals has at least these many happy numbers, or this percentage of happy numbers. And I can and the n sub I are growing rapidly, because at each step, you know, I need at least 10 to the n digits to get, to land in each interval. And just to simplify this, we can write this as e to a negative small number. And so the loss is about 1 at each step. And this allows me to produce an interval very far out, as far as I want. And so now that local limit law, like, I don't care about this big O of n to the negative 1/2 anymore, because it's only enough that it's little o of 1, that it's going to 0. Because I can make my interval out as far as I want. So yeah, I haven't been checking the time.
You have 2 more minutes.
2 more minutes, okay. Well, then at least let me state what my main result is. So I'm calling H a generalized B-happy function. So by this I mean we're in base B, and then I just randomly say H of 0 is 0, H of 1 is 1, and then H of 2 can be whatever I want. H of 3 can be whatever. And all I'm interested in is the mean and variance of 1 digit. And let's say that I'm interested in the density of numbers that go to a cycle C. Yeah, so I call it an integer type C if it eventually arrives at the cycle C. So happy numbers would just be type 1. I mean, this is just technicality. I'm just calling interval n strict if it's of this form. It's subset of b to n minus 1 b, and its size is exactly b to 3 n over 4. And then, and like I said, I can't, like, my theorem doesn't say anything if, like, for very small intervals. So we need at least an interval that is n strict, that is at least this size. And for most cases, like base 10 and squaring the digits, I think going up to like 10 to the 50th works. So, and what the theorem says is if there is an n satisfying this bound, and an interval I that's n strict, that has type C density D, then the upper density of the set of type C integers is at least d times this error term. And this is basically e to a small negative number. And so if n were, I think if n were like 400, if we took the case, we're looking at the interval of 10 to the 400 to 10 to the 401. For that n, the error is like, I mean, it's almost nothing. It's a millionth of a percent. So, okay, so that's it.
Very much. Thank you for a beautiful talk. Justin, we're glad to answer questions in private. Thank you.